Hi everybody, I'm Abby,
And I'm Alisa.
and today we'll be doing a presentation on the article entitled Rapid Screening of COVID-19 Directly from Clinical Nasopharyngeal Swabs Using the MasSpec Pen. So, the COVID-19 pandemic started in December of 2019, and since then we've developed two major COVID tests. The first one is PCR. It is kind of the gold standard and it detects the virus's genetic material in the body. It's the most accurate test we have on the market and it has a lower rate of false negatives. However, the con is that it has a long turnaround time and it might be a little uncomfortable to take. The antigen test detects the antigens on the surface of the virus or just the proteins there. And it's super quick, about 15 minutes total between when you take the test and then when you get your results back. However, it has a very high rate of false negatives, which is not great when you are trying to reduce the spread of COVID through testing. So the MasSpec has been used previously. It has been patented for cancer detection at the University of Texas, Austin. And so how this is done is they have a handheld pen that they put on different parts of the patient's body to determine if their tissue is cancerous or not. So how that's done is there's a water droplet inside the pen and that extracts all of the biomolecules from the tissue and transports it to the MasSpec for a real-time analysis of the tissue there. As the pen is moved around, more MasSpecs are performed and you can see which areas have cancerous tissues and which don't. This has been performed for ex vivo and in vivo cancer diagnosis, and it's been really promising so far. Picture now is Figure 1, which is a depiction of the entire process from collection of swabs to the MasSpec and statistical analysis. The first thing done in this experiment was to collect the swabs from the patients, and so the researchers did so with asymptomatic negative, symptomatic negative, and symptomatic positive patients. They stored the swabs in tubes without reagents, which is great because one of the downsides of PCR is that it is very expensive because of the reagents needed to transport the swabs. Not so with MasSpec pen. The swabs themselves had to be optimized to determine which ones worked best for analysis. And so the polyester flock swabs that were sterilized with gamma irradiation proved to be the best in this testing because there was no polymer interference in the resulting MasSpec. The other thing that they needed to change and optimize was transforming their pen setup to a reservoir, as you can see at the bottom of the figure. And so this was because they needed an increase of surface area. The pen just wouldn't capture all of the swab, and so they needed to transform that into something that could capture all the swab so that the solvent, mainly chloroform methanol, could be washed into the swab and then vacuum pumped out to the ESI source. ESI stands for the electrospray ionization, and what that does is it makes ion droplets that can then be analyzed by the MasSpec. All of this is done in 45 seconds, which is incredibly fast and would be very useful for COVID detection and diagnosis.
So now that we've covered that this study focuses on lipids, you might be wondering, what is the role of viral lipids? So all of the viral lipids that were focused on in this study is categorized under glycerophospholipids, which includes ceramides, lysolipids, which include lyso-PC and lyso-PE, and then just generally PE. So all of these glycerophospholipids are lipid messengers that serve as receptors and co-receptors for viral entry. So we can draw an analogy to the idea that lipids make up the phospholipid bilayer, just as viral lipids now compose the viral membranes. So viral membranes and viral lipids, specifically as components of such, protect genome-containing virus nucleocapsids from damage and facilitates the entry and exit of these nucleocapsids into a host cell. Specifically for this study, when looking at COVID, these viral lipids are also responsible for their roles in key replication cycle processes such as new virion productions. And these viral envelope lipids are obtained from the membrane of the host Golgi intermediate complex. So as discussed, the main method of analysis for this study is mass spectrometry. And really, I know my lecture has not focused on MasSpec with lipids yet. So we're going to talk about something more familiar to us, which is MasSpec with proteins. So MasSpec with proteins has beta and gamma ions that are represented in the peaks. So each peak is a different amino acid and its molecular weight. To obtain the whole molecular weight of the protein, we thus add each peak's molecular weight from either the beta peaks or the gamma peaks to obtain the whole molecular weight. However, with lipids, it's important to note that this is not the case. There's no such thing as beta and gamma ions differentiated because in lipid mass spec, each peak is its own lipid molecular weight. So now that we've reviewed what mass spec is relative to proteins, this is now figure 2a from the study that focuses on mass spec relative to lipids. Very chaotic and overwhelming. However, we're going to break it down. First, by the similarities that we already see between protein mass spec and lipid mass spec, which is present on the axes. So on the x-axis, there's a mass to charge ratio that's still present. And on the y-axis, there's relative abundance provided as a percentage. This is still the same from protein mass spec. It is also important to note that the solvent that's used for lipid mass spec is now chloroform methanol, and this will produce chlorinated peaks, which are mostly deprotonated due to the negative ion mode that's present, which makes the peaks negative. So the scientists of the study mainly focused on what was different between these three mass specs of asymptomatic negative, symptomatic negative, and symptomatic positive, and what peaks represented the negative versus the positive, and what they could focus on in the specificity of these lipids. Another thing that I wanted to note was when looking at one mass spec, say the topmost mass spec, you may realize that for one single lipid, there's several peaks. Let's focus on lyso-Pe, for example. So for lyso-Pe, which is represented by this green, there are two peaks on the left. You can see 452.7278 and 480.309. So you might be wondering, like I did, why are these peaks different and representing yet the same lipid? And the reasoning for this is because lyso-Pe has a ratio that can differ between its molecular weights. So the ratio of 16:0 for lyso-Pe is represented by the molecular weight of the peak of 452. However, the peak at 480 is represented by lyso-Pe 18:0. So the difference between 16 and 18 in these two ratios are representative of the two carbons that differ between the lipid of lyso-Pe. So carbon's molecular weight, as we know, is around 12. So if we multiply this by the two carbons that are differentiated between the ratios of 16 to 18, we get a difference about 24, which is the difference that we see between 452 and 480. So as was previously discussed, the scientists zoomed in on, if you will, these lipid mass specs and specific peaks that were different between the three mass specs that were provided. So the first specific lipid that they focused on was lyso-Pc with a ratio of 18:1, present on panel B of this figure at 556.318 mass to charge ratio. And so they identified lyso-Pc as symptomatic positive for both classifier 1 and 2. In contrast, in panel C of this figure, they identified lipid Pe 34:2 at a mass to charge ratio of 714.509. So this is contrasted against lyso-Pc because this is indicative of the negative, both symptomatic and asymptomatic, mainly for classifier 2, because all negative is what is being compared to symptomatic positive for classifier 2.
So now we're going to switch focus and talk about the statistical methods behind this experiment, also called LASSO. LASSO is the acronym for Least Absolute Shrinkage and Selection Operator. And shrinkage is where data values are shrunk towards a central point, sort of like a mean. So we've got a lot of terminology here that's going to be really important in understanding the analysis of the mass specs. The first ones are specificity and sensitivity. Specificity is the percentage of people who were actually tested negative who actually tested negative. And so all of these were confirmed by PCR and then compared to the lipid analysis. And so the percentage that did not test negative, that were negative, is then the false positive rate. For sensitivity, it's the percentage of people who were positive that actually tested positive, also the percentage of true positive people. The rest of that percentage not included is the people who tested false negative. The AUC is the area under the curve, and the ROC is the receiving operating characteristics. Both of these determine the accuracy of the measurements taken. FNR is the false negative rate, and FPR is the false positive rate. So figure 3 has been split up into two parts, classifier 1 and classifier 2. Parts A through C represent classifier 1. This is defined as the asymptomatic negative patients versus the symptomatic positive patients. And so in part A, we can see the AUC, or the area under the curve again. It has a value of 0.852. And so for AUC, you want a value that's close to 1 because that represents that you have a high accuracy in your data. For your ROC, you want your curve demonstrated by this kind of gray arching line to be as close to the top left corner as possible. And that makes sense because if your AUC is 1, then the entire graph would be covered. So you want as much of it covered up towards the top left corner as possible. And so on your axes, on your x-axis, you've got your false positive rate, which is really important, also defined as 1 minus specificity. And then your y-axis is your sensitivity, also your true positive rate. And so then moving on to part B, there's this little gray line in the middle, and that's your threshold. For B of figure 3, it's 0.350. That's determined by Lasso, and everything above that threshold is considered positive for COVID. Everything underneath that threshold is considered negative. The last represents the data values for sensitivity and specificity. And so the sensitivity for classifier 1 is 76.6%. And so that means that 76% of the people who were positive actually tested positive, and that other percentage was negative. This was not as sensitive as classifier 2 and thus had more false negative results. The specificity was at 86.6%. And so that means, again, that 86% of the people who were negative actually tested negative, and the rest were identified as false positives. This is more specific than classifier 2, which results in fewer false positives. So now we're moving on to figure 3, parts D through F. And again, this represents classifier 2. This is the symptomatic positive people versus all of the negative people, the asymptomatic and the symptomatic negative people. And so the sensitivity of this is 81.8%. And so that means, again, that 81% of these people who were positive actually tested positive. This is less than the false negatives accounted for in classifier 1, which is better. Specificity, however, is lower in classifier 2 than it is in classifier 1, which means that there are actually more false positives. This is represented by 77.21% versus 86.6%. And you can go back to that previous slide just to clarify that. The AUC is actually better, as you can see in part D of figure 3. And so this AUC is 0.879, which is greater than the last one, meaning it's slightly more accurate. Again, the ROC is up close to that top left corner, meaning that, again, the data is accurate. The threshold for this one in part E is 0.0201, and again, everything above that tested positive for COVID, and everything underneath that tested negative. Part F, again, represents what we covered in sensitivity and specificity, just in a more representational form.
So figure 4 reiterates what was shown in figure 2, just in a different format. So 4A is classifier 1, asymptomatic negative, symptomatic positive, and 4B is classifier 2, all negative and symptomatic positive. So as we were indicating between the positive and negative peaks as present in MasSpec, we are now showing positive versus negative indicating lipids in this format. So the same lipid is being focused on for positive indicating lipids, lyso-Pc 18:1, which is shown as a blue that is seen at 556.32 for its molecular weight. Whereas for negative indicating lipids, we are also focusing on, once again, lipid Pe 34:2, which is present on the left side of the figure at 714.51 and 794.51. It is important to note that although there were other lipids, such as various ceramides that could be identified as classifier 1 and various lipids that were also classified as classifier 2, such as lyso-Ps or DG lipids, these two, lyso-Pc 18:1 and Pe 34:2, are the ones that these researchers specifically focused on because you really want to focus on specific lipids when considering these tests. So now this is Table 1, which represents patient demographic information for the samples used in LASSO, and it serves as a comparison point between CT, PCR, and lipid analysis. So we should talk about CT and how first it was used to show positives. However, PCR was soon derived and was able to provide us with a differentiation between negative and positive results. And this is because PCR is able to detect viruses' genetic material in the body. And because it can detect this genetic material, it's more specific. It can differentiate between viruses as a whole and COVID specifically. However, this is also the reason why CT and lipid analysis is more comparable than to PCR and lipid analysis. And that's because CT and lipid analysis both take into consideration viral inflammation. And this viral inflammation is not as specific as PCR can get with the genetic material. Rather, it's on a broadened scale. It focuses on viruses as a whole, and viral lipids are used within these viruses. It's not just COVID-19 that it can pinpoint and focus on. So in summary, the MasSpec pen in relation to PCR is both more cost efficient and quicker, and then relative to antigen COVID testing, it's more accurate. However, throughout the study, we shouldn't negate the room for improvement that can be made, which is mainly on false positive results. And this can be seen due to the specificity of classifier 2, which is lower when we take into consideration all the negatives, both symptomatic and asymptomatic, and the heightening of the false positives. However, it is important to note as well that lipid analysis allowed for lower false negatives than an antigen rapid test, which is another great pro of this analysis method. Further improvements obviously can be made to improve upon the false positive results, and as a means of such, we can make greater the sample size, and in turn, we can discover how to lower the false negative results and the false positive results, which would improve just lipid analysis as a whole. And these are our references. Thank you!